All right, good morning, everyone. So today we're going to start a new unit on neural networks, at least what we call shallow neural networks, or multi-layer perceptrons. So our motivating problem here is just sort of a simple toy problem where we have data that looks like this. So we have two-dimensional feature data, x0, x1, and the labels are either 0 or 1, so there's a categorical problem. And you can see that we have some green points in the middle and blue points around the side. And from our study of these types of data sets in the last couple units, we know that this is not linearly separable. So there's no way that I can make a good linear classifier that's going to give me a decent error rate. So the question is, how do we handle this? So in the last unit about support vector machines, we learned that we can do some sort of feature transformations as a first step. And if we do a clever feature transformation, we can make the data more linearly separable. Maybe not perfectly linear separable, but much closer to linearly separable than this original data. And then later we can apply linear classification on those transformed features to get a decent error rate. So in the last unit, we talked about several kernel methods that do this for us. We had like RBF kernel, polynomial kernel, and so on. But a good question is, well, how do we know which is the right transformation to use for a given data set? Because in practice, the data set's going to be much more complicated than this, and it's not going to be clear what the right transformation is. So the main idea now is, can we learn a good transformation directly from the data so that we don't have to know, you don't have to have some like domain physics knowledge of the data in order to choose that transformation. So that's the whole goal of the next couple units, is learning a transformation such that we can do good linear classification or regression. So that's the main idea. And so in this unit, we're going to focus on a two-stage approach to classification, where in the first stage, we're going to learn, this is for this particular example, we're going to learn 4 transformed features. And then, second stage, we'll apply linear classification to those transformed features. Okay, so how are we going to build these transformed features? There's many, many possible ways to do this, but we're going to use something that's kind of familiar. The transformed features will each be the soft output of a linear classifier. Okay, so what do we mean by soft outputs? We mean values somewhere in the interval between 0 and 1. A hard output would mean like either 0 or 1, nothing in between. But a soft output means it could be like 0.4, 0.9, could be any such value. And typically when we have these soft outputs, we think of them as probabilities. We think of outputting 0 as like saying the probability that the label y equals 1 would be 0. Or 0.5 would be the probability that the label equals 1. That event is 50% probable. So we can think about these soft outputs as probabilities. In any case, again, the first stage will output 4 numbers, each between 0 and 1. And the second stage will take those 4 numbers and perform a binary classification on those new features, 4-dimensional feature vector. So let's try to visualize how this is going to work out. So this picture here is illustrating what happens in the first stage. So remember that each of our features that we're outputting in the first stage is the soft output of a linear classifier. So let's think about what a linear classifier looks like in 2 dimensions. We can think of the linear classifier according to a decision boundary. So here we have 4 different decision boundaries because we have 4 different linear classifiers. And for each of these linear classifiers, the values on one side of the boundary will be closer to 1, values on the other side of the boundary will be closer to 0, and the values right on the boundary will be exactly 0.5. Right? That's when we're 50%, we're completely unsure. So now, this picture down here shows exactly, for those 4 different classifiers, exactly what the soft output is versus x1 and x2. And we have to interpret the color here. So here's the color map. So white would be 0, dark red would be 1. So if I look at this picture, this is going to be the very first of these 4 transform features. And you can see that this one corresponds to this boundary. That boundary would be right here. That's where it gives us 0.5 output, or 0.5 probability. And so from this figure, you can see that as you go left of that line, you're going to be outputting numbers closer to 1. So let's just write, I'll do it over here. So on the left of the line, I'll write a 1. To the right of the line, I'll write a 0. Now, remember that there is a gradual transformation. It's not like it's 1 exactly here and 0 here. It gradually transforms from 1 over here to 0 over here. Gradually comes down. So there's sort of a soft transition. So this is the line here. The next one you can see corresponds to this line. And down here you can see that the 1s are here and the 0s are here. So maybe I'll write this over here. So 1s are down here, 0s are up here. And the next one corresponds to this line. And now you can see that the 1s are down below. So 1s, 0s. And here we have this final line with the 1s to the southeast. So 1, 0. Okay, so that's what each of those individual classifiers is outputting. Some number between 1 and 0, where, for example, here, the 1s would be far to the left, 0s would be far to the right. Now, if we think about the vector that's outputting as a whole, we can see that 4-term vector essentially tells us which of these regions we're going to be in, right? Because each of those regions has a unique 4-length binary vector that categorizes it, or characterizes it. So the one in the middle, this region, which is actually really what we're after, that's where the green points are. This is going to be, so let me write the vector here. So it's going to be 0 because we're to the right. So with the first feature, we're kind of, we're less than 1/2. For the second feature, we're also less than 1/2, so I'll put another 0 there. For the next feature, we're actually greater than 1/2, so I'll put a 1 there. And for the final one, I'll put a 0 there because, again, less than 1/2. Okay, so if I characterize each of these regions by a 4-term binary vector, then the one in the middle corresponds to 0, 0, 1, 0. Now that does not mean that the vector of values is exactly 0, 0, 1, 0 everywhere in there. It's going to be some numbers that are, the first two will be closer to 0 than they will be to 1. The third will be closer to 1 than to 0, and the last one will be closer to 0 than to 1. But as I move this point around here, I'm going to get different values for those 4 features, right? But anyway, this is roughly speaking how we can think about this. We can think about it as an intersection of half spaces. That's, I think, a useful way to think about it. Because we're taking this first half space defined by everything to the right of the first boundary. We're intersecting that with the second half space, which is everything to the northeast of that one, and intersecting that with this third half space, and intersecting that with this fourth half space. And when we intersect all those 4 half spaces, we get this interesting region here, which is where most of the green points are. So this is another way to think about it. And then finally, we haven't really talked much about the second stage, but once we get these 4 numbers that are output from the first stage, now we can think of this as a standard classification problem to which we can apply logistic regression. So we have 4 features coming in. We just need to come up with a weight vector 4 by 1 and an intercept term b. We need to adjust those so that it's going to output values greater than 0.5 here and values less than 0.5 all the way around the outside. And when we do that, we get this picture here. So again, look at the color to tell the value. So the dark red is about, close to 1, white is close to 0, and you can see that it's outputting dark red or a high value all the way around here, and it's doing a very good job of capturing that decision region. In fact, it's doing a better job than you would expect just from these 4 crude lines. It's actually quite circular, which looks like it matches the data better. So this is the main idea. If you understand this slide, then I think you'll understand the main idea of how these neural networks work. You do 2 stages. The first stage is coming up with some interesting, useful features, and the second stage is just linear classification or linear regression as we learned it before. Okay. Yes?
So for the first stage, it says you learn 4 transformed features. So is that basically just instead of applying this x1, x0 value to the data point, you're applying these probabilities, and that's the transformation?
So yeah, what I didn't tell you yet is that the exact locations of these lines, this was not something that we made up. This is something that was learned from the data itself. So this is just kind of what happened. We set up this scheme. We define the likelihood. We do maximum likelihood, optimization with some sort of gradient descent algorithm. And at the end of the day, this is what it decides to do. So we can think of the first stage as taking in the raw x values and producing these features. We're going to call them A 0 through A3. And the second stage takes those 4 numbers and does linear classification to produce this output A, this final value. And if we look at the total input to output behavior of this entire network, you see this is how it takes in the x's, and this is what it puts out at the end after these 2 stages. Does that answer your question?
Yeah.
Okay. Yes?
So for a higher dimension data set, is there any intuition of knowing how many transform features you can start with? So say you have x, 1 to 4. How do you choose, or how do you learn how many transform features you need to have?
Yeah, that's a good question. So I think we'll talk about that later, but generally speaking, you tend to increase the dimension. So if you start with D features at the beginning, like here D is 2, then you increase to a higher dimension. And then later you decrease to the final dimension that you need for the problem you're solving. So if we're doing binary classification, we're always going to reduce to 1 at the end. If we're doing classification among 10 classes, we're going to reduce down to 10 outputs. Each one of those outputs tells us the probability that's in that class versus the rest. But the number of the what we call hidden ones in the middle, that's a design parameter. That's something we want to optimize according to a bias variance trade-off. We could do experiments, various experiments with cross-validation to figure out how to choose that. We'll talk more about that in later slides. We'll get into all those details.
And then the metrics on the plots in the bottom left. What is there any the titles?
Oh yeah, okay. So what I'm showing here, these are actually the weight values of the second stage weight values. And I didn't plot out the intercept, but there's also an intercept there. I guess what you can confirm about these, that the first, so whenever you see a 0 here, you expect that the weight value to be negative, and whenever you see a 1 here, the weight value should be positive. We see negative, negative, positive, negative. So that's making sense. There's also an intercept term in there as well that's kind of explaining why a 0 should be like a negative and a 1 should be positive. The intercept is going to kind of put us in the middle, but I don't know if that makes sense. And then, yeah, the first thing is just what we're plotting. We'll establish this notation in the next slide, but these are like the hidden activations, as we call them. And this is the output activation. But we'll see that in the next slide. Okay, any other questions so far? Okay, so let's view this from like a block diagram perspective and introduce some notation. So here's our two-stage network. We're going to call the first stage the hidden layer and the second stage the output layer. We call this the hidden layer because, really, if you just think about the input to output behavior, there's some hidden variables internal that are being worked on, but if I just show you like something like this, it's not really clear what's going on inside. So that's the hidden layer. And so when we look at this, we see, let's focus on the output layer first. So these are the 4 features that we started with our two input features, we transformed to these 4 features. And then everything here is just basically logistic regression. So in logistic regression, you take those inputs, you apply a weight vector, add an intercept, and that gives you your score, your linear score. And then you put that score as a real number. If you want to convert it to a probability, you put it through a sigmoid, and that converts it to a number between 0 and 1. And now we can view this as a probability. So these A's are activations. So we have a subscript O for the output things and a subscript H for the hidden things. So this is our output activation. And the output activation is the final probability that Y is equal to 1 versus 0 given the features X. So that's what the network is delivering at the end. And then, we have a linear score, which is a real number. And here are our 4 activations that we got from our transformation. Now, is that clear about the output stage? Okay. So, output layer is logistic regression. Now, the input is actually quite similar to logistic regression as well. In fact, if I just think about like how I'm computing any one of those activations, then this is exactly logistic regression. Looks just like the output layer. So you're going to have your input's coming in. Actually, to get those inputs to go to here, there's just going to be one of the rows of this matrix multiplying x, and then you're going to put it through this sigmoid. That's going to convert the real number to a probability between 0 and 1, and that's it. So it's like you have, this is again linear classification according to logistic regression. And then now you have a different linear classifier here. And you have a different linear classifier here, and one more linear classifier here. So that's how we got these linear boundaries, and then these are the, once we put it through the sigmoid gives us this smooth transition from high to low. So we have 2 stages. Again, we're using Z like always for the scores, but now we have scores here and we have scores here, so we put a subscript H for the hidden ones, subscript O for the output ones. And we're going to refer to the nonlinear parts of this network with the variable H, just a function. And so something I want to point out here, just with the notation, we're taking in a vector, we're outputting a vector, but I'm using a non-vector or non-bold quantity here. And what I mean by that is that this function acts element-wise. So I apply this sigmoid to the first coordinate in the input vector, to the second coordinate, to the third. I do that separately, and that's how I get the first output and the second output and so on. So you can see the separable nature just from this picture. It applies on each element individually, but there's no, mixing across elements. Yeah, I think that's, so in terms of the terminology, sometimes this is called a 2-stage feed-forward neural network, but another common term is a multi-layer perceptron. So the overall structure we see is linear transform, simple nonlinearities, linear transform, simple nonlinearity. That's the overall pattern you tend to see in neural networks. Question?
So in the hidden layer, we're using 4 ways to linear transform the features. Yeah. So how do you know that, like the different 4 weights, the WH?
How do we choose 4, or how do we train the parameters?
Yeah. How do you train the parameters?
Yeah, we're going to talk about that in the next slide. But we're going to use maximum likelihood like always. Same way we always do it, but yes. And how did we choose 4? We could have chosen more than 4. We could have chosen less. Let's think about what happens if we would have chosen 3. Do you think that would have worked well based on this picture? It would have made a triangle, right? Probably that would have worked pretty well. What if we had only chosen 2? Would that have worked well? No. Because 2 will just give us like some region that, would be, it wouldn't be like a closed region. It would, the red would be going off and we'd be making a lot of mistakes. So here you can see why, it's the more of these that we use, we have a more sophisticated shape. If I would have used 5 or 6, I could make this even more and more circular. I could make it so that it's more customizable to the data. What do you think would be the disadvantage of doing that, based on what we've learned so far in the class? What? I didn't hear.
Oh, training time.
Training time, yes, but there's another more fundamental issue.
What, overfit?
Overfitting, exactly. Because essentially we would be adding a lot more parameters that we have to learn, And for a finite data size, we could eventually overfit the data. We could, there's questions about that we can use cross-validation to figure out what is a good size to use. Okay, great. So any other questions on this so far? So we have the network architecture now, getting to the training, the model. So if you think about what we have to design, we have to design these weights, these intercepts, these weights, and this intercept. Everything else is determined by the architecture. So let's take all those designable variables and just put them all into this quantity theta. So theta will be all of our unknowns. And as always, we want to fit our theta using some training data set which we've been given. So we have a bunch of feature label pairs. So we want to use the same approach as always, maximum likelihood. So we have to start by saying, what is our likelihood function? So for the ith sample in our training data, we could say the probability that yi equals 1, given the feature vector I and the parameters theta, is going to be this. So this is actually just reflecting the very last stage. This is the sigmoid on the very last stage. And here's z output. This is the variable going in to that very last stage. So here, the likelihood is really just entirely defined by this when we're writing this. But then we have, okay, this thing, this output, is somehow related to the input using all those trainable parameters with this big function f. And that function f describes everything here. Function from x to that last zo is in that big function f, and that includes all of our trainable parameters. Okay, so this is the likelihood function. Again, sigmoid, written in terms of the output variable, the output variable written in terms of the input variable through f, and that is where we see all these parameters. So finally, to do this maximum likelihood, we set up this problem. We say, find the theta that minimize the negative log likelihood for our entire training data set. So we're going to have the sum over all of our samples, and then we have the negative log likelihood for the ith sample. And that's just going to be, if yi equals 1, then we have negative log likelihood of this. If yi equals 0, then we have negative log likelihood of 1 minus this. And we did that derivation back in Unit 5, where we simplified this expression down to this one. So this is our binary cross-entropy loss, log of 1 plus e to the power z minus yi/z. So this is what we have to optimize. We would like to do some sort of gradient descent, where at every step we take the gradient of this expression here, and then we move a small direction in the negative gradient direction. As we'll see, taking the gradient of this is a little challenging because of this multi-stage network. We have a lot of things going on. So what we're going to have to do is we're going to have to come up with a very organized, systematic way to compute gradients in these multi-layer functions, and that is called backpropagation. So we'll go through the backpropagation later in this unit. But that will give us the gradients, and then the gradients can be used in gradient descent, and then we can minimize our likelihood. All right, that's the big picture. Any questions so far? Okay. All right, so why do we call these things neural networks? Well, basically because in the mammalian brain, it works in a similar way. So what we see in the brain is you have these neurons. Roughly speaking, here's like a neuron. It has a lot of inputs that come from many other neurons, and then it has an output that it sends to another neuron. And the way that this functions is there's some charge that flows down these things called the axons. And then once enough charge accumulates at one of these, they call the soma, all of a sudden it surpasses a threshold, and then it sends out a big charge out. So in terms of a block diagram, we could think like this. So this is sort of like the charge coming from all the other neurons. This accumulates together, and once that charge exceeds a threshold, then you send a pulse out. So, and if you look at this is very similar to one stage in our neural network, right? It's in fact identical to this. So here's the charge coming in. Here's like some sort of relative weighting of those things. And then we have this shape where once things accumulate beyond a certain point, we get a big output. So because there's that similarity, you can think of these as inspired or similar to neural networks. So people call them artificial neural networks. So again, the main idea, output when the sum of input currents reaches a threshold. Okay. So just quickly, a little history. So obviously, humans have been interested in the brain for thousands of years. In the 40s, this guy, Donald Hebb, came up with like a simple model for how these neurons work, how the brain learns things, similar to what we saw on the previous page. And then in the 1950s, people said, well, maybe we can use this in sort of an engineering computer science way. And so this guy, Frank Rosenblatt, coined the term perceptron. And basically what he was describing was like a single layer network, which, as we know, is very similar to logistic regression, essentially the same thing. And so back in the 50s, when computers just started to come into existence, they did some very simple computer implementations, but of course, everything was very limited in those days, and as we know, linear classifiers themselves are quite limited. So then, in the 1960s, as they got more power and more experience, they said, okay, can we cascade these into multi-layer networks? And can we figure out a way of doing this gradient computation through an organized sequence of operations called backpropagation, which we'll learn about. And then that stuff kind of died out. People got, originally they were excited and then they weren't so excited. And then in the 1990s, people got very excited again. A lot of progress was made. In those days, they had more compute power, more memory, but then didn't really lead to very, very much, and so people didn't get excited anymore. So like in the 2000s, if you told someone you were working on neural networks, they would have thought you were pretty crazy. And then now we're in the third wave of all this, roughly speaking around 2012. And in many ways, what we're doing now is not so different than what we were doing in the 1990s, but we have much more computational power and we have much more data. And those things come together to, they originally came together in around 2012 where there were some real breakthroughs in speech and in image processing. And that got people very excited because all of a sudden these neural networks were outperforming all the other methods that had been designed by considerable margin. So people said, wow, okay, maybe we should invest more effort into that. And so a lot of people started working on it, and then very fast progress started being made in many other fields, a lot of the theory and everything. So that's kind of where we are now. We're in this kind of revolution, and who knows how long it will last, but maybe it will die out again and be revived in another 30 years or so, but we'll see. Certainly right now, it's still very productive. People are making a lot of progress, a lot of breakthroughs, doing a lot of neat things with it. All right. So, okay, so let's talk a little bit more generally now about how we can construct these networks. So far, we just saw one example, but there's a little bit more freedom, or more generality. So in general, we're going to have D inputs in our vector X. So this is we've used this notation D since the beginning of the term. So in general, we're going to have D-dimensional raw feature data. Then we're going to have this hidden layer, and here's the linear equation. This is how we compute our scores, and this is the equation for the Lth score. And so we have like the Lth intercept and the Lth row of the weight matrix. And then we're going to put that through some nonlinearity. We used sigmoid before, but that's not the only possibility. We can use other stuff too. So we're just going to call this H sub H. So the sub H means the hidden. So this is going to be our hidden activation function. We're going to talk a little bit more about how to choose that in a moment. But the key point is that it's nonlinear. Let's think about why it needs to be nonlinear. So go back to here. So what happens if these guys here are linear?
Is that just the same thing as doing the linear transform before?
Yeah. So because if you compose linear functions, the result is linear. So if this is linear, and then I do another linear, and then I do another linear, essentially I'm just doing one linear thing in 3 stages. And at that point, I'm back to logistic regression. Linear followed by sigmoid. So it's super important that these are nonlinear. That's what makes this thing work. And this is essentially like one of the simplest nonlinear things you can do. Like of all the possible nonlinear transforms between this vector and this vector, it's a very much of a simplification to just say, I'm going to do that nonlinear transform element-wise, and I'm going to use the same element-wise transformation every time. And also the sigmoid is a very nice, smooth, simple nonlinear transformation. So overall, it's like this is one of the simplest nonlinear things you could possibly do to go from here to here. And in many cases, this is enough. This is enough of a nonlinearity to get things to work quite well. Okay, but we will have other possibilities, and we'll talk about other options for that nonlinear activation function. And another thing we have to choose is how many hidden units. We talked about that briefly. That's going to be a design parameter for us. And we're going to call that D sub H. Then we come to our output layer. We're going to have possibly a different nonlinearity there. We'll call it H sub O. But I want to emphasize that actually it's optional to put it in. Let me show you again, in this case, why that is. So the transformation from Z to A given by this sigmoid is invertible. I'm just basically taking the real line, and I'm squeezing that to the interval between 0 and 1, and I can unsqueeze it back without any loss of information. So in other words, if you tell me this value, I can easily get this if I want. This last thing is not really doing anything for me. It might be helping the interpretation. It allows me to draw something like this on a scale from 0 to 1, but there's actually no new information here. So if we would have wanted to skip this, just get rid of this, and build our network that way, that would have been fine. We just have to remember that this is a real number instead of a probability, and we just have to change our loss function. Essentially, we would take this stuff and put that into our loss function instead of explicitly representing it as part of our network. So we could do the same thing without it. So that's what I mean over here when I'm saying that this output activation function is optional. You can put it in or not. But either way, you have to make sure that the loss that you choose is matched to whatever you chose for this output. So if you have the softmax, the sigmoid, if you have the sigmoid here, then you build your loss. In fact, let's go back to how we built the loss over here. So actually, when you look at this loss function, you can see that I'm only using Z, right? Z output. So that's actually the last thing out of the network that I'm using. I'm not even using the A output. So if I do want to use the A output, then I actually have to use a slightly different version of this that we haven't seen yet, but it's just the corresponding version after Z is put through that sigmoid. So it's a different formula, but it's at the end of the day, it should give us the same likelihood and everything. Okay, so, and finally, what about the number of output units? This really is not a choice. This is determined by the problem itself. So if I'm doing binary classification, I just want one single output. If I'm doing classification of 10 classes, I want 10 outputs. If I'm doing regression with predicting one single target, I want one output. So this is not a choice. But this, DH, that is our choice. Different choices will have different performances, but that is something we can choose. So this is often how people draw these networks, and it's a little bit different than how we typically draw things in electrical engineering, so I want to point this out. So here, like in electrical engineering, often the functions, the functions are given boxes, and then the variables maybe are not given a box. There's just sort of a line going into a function. But as you can see over here, it's sort of the opposite. The variables are given these boxes, and the functions are represented by the lines. So in other words, on the left here, this input, that would be the vector x. This is like x0, x1, x2. And then the hidden variables, these are actually the hidden a's. So you have like AH0, AH1, AH2, AH3. And then finally the outputs. This is A output. And all this other stuff here, this is described just purely by those arrows. So those arrows are performing all of this processing. And similarly, all of this processing performed by those arrows. Okay, so that's how almost all the pictures you'll find about neural networks look. So I had to draw this one myself. Couldn't find any others out there. But I think from an electrical engineering standpoint, this is how we are used to seeing things. So I think it's still useful. Okay, and the final comment is we can definitely use more than 2 layers. And when you use more than 2 layers, I guess you could call it a deep network. Deep networks can have dozens, even thousands of layers. But we're just going to focus on 2 because it's enough to describe the main concepts that we need. And we'll spend next unit, Unit 9, on deep networks. But for now, this unit is all about these 2-layer networks. Okay, any questions so far? All right. So here's a slightly more general picture where we have, the only thing different in this picture is, in this picture we'll have possibly more than one output. And we'll have a little bit more generality in how we build that output activation. But otherwise it's the same. You start with a certain number of inputs, D, we've been calling them, and put it through our linear transform. So we do a matrix multiply, we add a vector of intercept coefficients, and then we get DH, new variables. We tend to put each of those individually through an activation function, and then we get our activation variables. Those act as the inputs to our next linear transform. We get our output scores, and finally we might do one more nonlinear thing to get our outputs. Now this one here, if you notice, I'm using a bold-faced function. So this is a function that takes in two variables, returns two variables, but it may not operate element-wise. It might be more sophisticated. And what I have drawn here is the softmax. So the softmax, if you remember, it looks like this. So A, O, call it J, is going to be e to the power ZOJ over sum over L, E, Z, O, L. So this is a function that takes in, and then this is J going from 0 to D output. It's a function that takes in several variables and gives several variables. So this is plotting, let's say for the first J, in the case that there's two of these. So you have Z ZO1, ZO2. And when ZO2 is large and ZO1 is small, you get a big output this way. On the other hand, when we look at this, when ZO1 is large and ZO2 is small, you get a big output in this node. And so this is exactly how that softmax works. It looks at this vector of real numbers, and it tries to find the largest one. And the largest one, like if the first one is the largest, it will put a big output in this direction. But overall, based on the way this is constructed, these numbers are all between 0 and 1. And when you add them up over all the j's, they sum exactly to 1. So this finally is a probability mass function across those DO possibilities. So with the softmax, this is a PMF. Whereas this is a real number in D0. So that's what the softmax does. We learned all about this in Unit 5. And that is the typical choice that in a neural network you put here if you're doing a K class classification with K greater than 2. Okay, so otherwise I think, so the point here is that H can act on the full vector, but otherwise everything else in this picture is the same as before. The hidden ones act element-wise, but the last one is kind of an exception. It can act on the full vector. And of course, it's optional. You can choose not to have that. You just put out the ZOs, and then this is your loss. You put this, your loss takes in the Z's instead of the A's. or you could define the loss differently so that it works on the A's if that's your preference. And when you do this in PyTorch or TensorFlow, they give you both options. You just have to make sure that you're using the loss consistently with the variables that you're giving it. Otherwise, it won't work. All right. Okay, any questions on this slide? All right. So let's talk a little bit about the choices we have for these hidden activations. So the one that we've talked about so far is the sigmoid. This is the function. This is what it looks like. And this function is going from 0 to 1. We can think of the output as a probability. And when the input is 0, this takes on the value of 0.5. Okay. So at a high level, what you notice is that the outputs are bounded, but they're not centered. Like, by centered, I mean centered around 0. These are centered around 0.5. Like if my inputs were 0 mean, my outputs would have a mean around 0.5. So these are sometimes used in shallow networks, but there's a slightly better option. Instead of using a sigmoid, use a tanh. It's just a centered sigmoid. So you take your sigmoid from above, you multiply it by 2, so that it goes from 0 to 2, and then you shift the whole thing down by 1. So finally, this goes from, it goes from basically -1 to 1. So now it has the same shape, except that the outputs are centered. And centered is, it tends to work a bit better with some of the other assumptions in the way that these software frameworks are designed. So like PyTorch is designed to work best when the inputs to the different layers are centered at around 0. And so you'll find if you use a sigmoid and a tanh tends to work a little bit better than a sigmoid. But otherwise, they have essentially the same shape, so they're similar. Okay, we'll talk more about why later. It has to do with the fact that it's a non-convex optimization problem. We're not guaranteed to converge to the global minima, so you need a good initialization to converge to a good minima. And there are some initializations that are put in there, but they're designed assuming the variables are centered. So if you give it non-centered variables or variables in a very weird range, too big or too small, you could get stuck in a local minimum. Okay. There's another very common option called a rectified linear unit. And this has a very different shape, as you can see. It goes from 0 up to up to infinity, just keeps going. And when the input is negative, the output is just the value 0. And when the input is positive, the output is just equal to the input. So the formula, you could write the formula like this. You just take the max of the input and 0. And so as you can see, the outputs are not bounded, right? It can be as large as the input. But there are some advantages to this. We'll talk about them a little bit later in the context of deep networks. These are definitely the most popular choice in deep networks. If you use these in deep networks, it doesn't really work very well. But these work great in deep networks, and they also work well in shallow networks too. So in your project, you can experiment with these different choices and see what you get. But there's something that's very nice and simple about this. It's kind of attractive. There are some issues with it as well. The fact that it's 0 here, it's basically throwing out all the information in a negative input. That has some consequences that we'll talk about later. Okay, so any questions on hidden layer? Okay, very last thing, let's talk about the, I'll save this slide for next time because it's going to be useful to talk about the loss functions as well. So I think that's enough for today. Any last questions about anything? All right, great. So we'll see you guys on Friday then.